All right, so today we're going to go through this messing with mixtures activity. We are just going to go straight through this, and we'll have the camera so that you can see what is going on in the lab with the lab materials. So the first thing it says, look at the items in bag A. What do you see? Well, to be honest with you, I don't have a bag for you to look at, but we have a cup for you to look at. So you might, if you guys want to flick the light out, you can. But when we look at this mixture, we have beads, and these are chickpeas. So if you ever ate hummus, chickpeas are what hummus is made of. Okay, these are pinto beans. Okay, so it's really just beads and beans. It's kind of hard to say separately. So when we come back to our document here, what do you see? I'm going to go ahead and put a text box here. I'm going to use a color so you can see what I type. I'm going to say I have beads and beans in a cup. Now, did I make that a sentence? That would probably be the right idea. So we're going to say I have beads and beans in a cup, and I could even give some more details. I have green and red beads and chickpeas and pinto beans in a cup. All right, so for this activity, though, let's read and continue. Okay, I feel like there's a lot of... So we can make it bigger. Is that better? Yes? Okay. I can make it even bigger if we need to. That's better? Okay. All right, so I have green and red beads and chickpeas and pinto beans in a cup. Okay, fine. The beads are the regular components of the soil. How many different types of contaminants are present in your soil sample? Okay, well, if the beads are the regular components of the soil, then I have, let's go back and look at it. I have the chickpeas and the pinto beans. Those must be contaminants because the beads are what we're actually looking for. So I have two types of contaminants. Okay. What is the total mass of your bag? Be sure to subtract the mass of the Ziploc bag itself. Record this amount in the mass of the mixture. Well, let's go back to the camera and kind of look at what we have. We have this cup here. So we need to know the mass of the cup and the mass of the stuff in the cup. So we're going to bring in our scale right here. Okay, and like we have done before, we are going to kind of turn our camera so that you can see. Hopefully that glare. That's too much. Okay, we'll see what happens. There, that's better. All right, so here's our empty cup. Let's go ahead and turn on our scale. We want to always hit tare to make sure that it's really at 0. Notice that we are measuring in grams right there. So we're going to set the cup on there. And the cup has a mass of 9 grams. So I'm going to go ahead and note that in my document. It doesn't say to do that, but I'm going to do that just for my own records. So I'll even label it appropriately. Empty cup equals 9 grams. All right. All right. So, but it asks for what is the total mass of the bag. So we're going to come back to the camera. We're going to take the empty cup and see what the total mass, the whole thing is. So 51 grams is the whole mixture. I'll come back and we're going to type mixture plus cup equals 51 grams. Then it says, be sure to subtract the mass of the Ziploc bag, which in our case it's a cup. Record this amount in the mass of mixture column of the chart. So I need to figure out 51 grams minus 9 grams equals what? 42, right? 42 grams. So I need that number in my data table down here. So let's look down at the data table, and I need to make this smaller so we can actually see the data table. So when we look, all right, the mass of the mixture right here is going to be the same for every part of our data table. It says record this amount in the mass of mixture column of the chart. So we're going to go ahead and type in 42 grams. Paper just jumped on me. We have 4 kinds of things. So we're going to put that in the 4 columns there. Now it says for us to separate the parts of the items and find the mass of each group. Use the following formula to calculate the percentage for each part of the mixture. All right, so let's go ahead and type in the items. If we go back to our mixture, we have red beads, chickpeas, pinto beans, and green beans. Okay. So then we're going to go back to the camera and show that separation. One of my beans is... Okay. So sort of a tedious part. In this case, we have a suspension mixture. So we have really chunky pieces that we can just pick apart with our fingers. Makes it a little bit convenient, but takes us a little bit of time too. Would it hurt anything if I lost a bunch of these beads because they fell on the floor? What would it hurt? The grams, right. My total mass would be very different if I lost a bunch of the beads. So we need to make sure that we are collecting all of our beads and make sure that we have accounted for every part of the total mass. Otherwise, our percentages would be wrong. And at this point, I'm wishing I had done just 3 things, but that's okay. This is probably the longest part of what you need to kind of consider, look at, think about. So as you can see, I'm just separating the mixture right now. I know this is super boring, but this is the way we have to do it. Okay. But this is also a good, solid, tangible example of like statistics and analysis. When you're looking at a group of data and you want to separate out the parts, sometimes you do that physically, like we're doing here, and sometimes you would do it with numbers or with categories instead of actual physical beans and beads and such. Okay. So I'm going to gather up the red beads since that's the first thing that we put on our list. I have all red beads in my cup. I'm going to put my cup on the scale. And we can see that it's 16 grams. Is 16 grams the mass of the beads? No. So in my data table, I'm going to go ahead and mark that. I'm going to put 16 grams minus the 9 grams, which was the cup, equals 7 grams. That's the mass of the red beads. So make that a little bigger so you can see the words, the numbers. All right, so let's get the mass of the green beads since they are next on the list. We'll go back to the camera to look at that. Yes. On this chart, what was your question? No, there's another one. There's a percent mixture. So that's actually what we're going to work on today. That's actually today's lesson. So we just have to get to there by separating out our mixture. Okay, so the green beads we have on the camera, 13 grams of green beads. Now, once again, is that just the green beads that's 13 grams? No, what do we need to do? Subtract 9 because that was the mass of the empty cup. So we're going to go 13 grams minus 9 grams equals okay. We'll continue. So like I said, this is sort of the tedious part of this percent composition is separating it out in real time. But we need chickpeas, so let's go back to our camera. We have 31 grams with the cup and the chickpeas. So we're going to do the same thing that we have done. 31 grams minus 9 grams equals 22 grams. Okay, all right. We'll grab these pinto beans. And then we'll come back to camera shot. 16 grams for the pinto beans and the cup. So suppose I could have just copied this one, but all right. Do you guys need a minute to make sure you have all the numbers? Yeah? Okay. All right, so let's look and see what we're supposed to do with this. So it says calculate the percentage. Calculate the percentage for each part of the mixture. Record your data in the chart. Mass divided by the mass of the mixture times 100 is the percent of the mixture. So we're going to take the mass of the stuff that we had divided by the mass of the total mixture times 100. So I'm going to pull up my calculator and kind of show you what that calculation looks like. Standard so it's easier to see. All right. So for the first one, we're going to do mass divided by mass of mixture times 100. The first one is 7 divided by 42. 7 divided by 42. So that gives us 0.16. If you don't remember to do the times 100, you're going to get a decimal. When you do times 100, that gives you a percentage. So we're going to round that off to a whole number because all of our other numbers are whole numbers. So what would that round off to? 17. Okay. And then here's a cheater trick. If I know that my mass of the red beads was 7 grams, and my mass of my pinto beans was 7 grams, then I know that both of these percentages are the same. So I can go ahead and just use that same calculation. All right, so let's look at that again. Mass divided by mass of mixture times 100. If we pull up our calculator again, our next mass is 4 grams. So we're going to go 4 divided by 42. Why are we using 42 for the mass of the mixture? That's all of it. That's the total mixture. And then we have to times 100. Otherwise, our numbers won't make sense. And we're going to round that off to a whole number because all of our other numbers are on a whole number. Okay. All right, and the last one, 22 grams divided by 42 times 100. So 52. All right. So this says check your answer by adding up all the numbers in column 4. The total should be 100 because all the parts of your mixture combine to make up the whole mixture. Well, let's check our answer by doing exactly what it said. 17 plus 10 plus 52 plus 17 equals 96. Why doesn't it equal to 100? It's pretty close. It would round to 100. Remember all the rounding we did? With every number, we rounded it off to a whole number. That is what causes rounding error. So when you come really close to 100 statistically, then you're pretty good. If we came up with a number that said like 82 or even just 90, then we'd have to go back and check our work. But because we rounded all of these numbers, we know that 96 is pretty good. So we're going to write 96%, and then we're going to put in parentheses rounding error, because I want you to know what a rounding error is, but also because it is a thing. And mathematically, statistically, rounding errors can mess you up if you don't remember that they're there. Okay. So then the questions. Okay, well, that's all fine and good, but why would I ever use this? What percentage of the soil was contaminated? Well, that question comes out of the blue. Let's come back up and look. If the beads are the regular components of the soil, how many? So the different things are the contaminants. If we look at our beads, we only had 27%. So these two numbers together, 27% of soil. The rest of it, 52 plus 17, so that's 9, 69% of it was contamination. Would that be a good soil to put a garden in? Would that be a good soil to play on, to let children play on? Depending on the contaminant, but I'm thinking probably not. So 67% of our soil was contaminated. So you can kind of see where trying to find the percentage of the mixture can be very important for different applications. So what situations would a contaminated soil sample be of concern to engineers? What can you think of? We just talked about it might be a concern if the engineers were building a playground or a garden. Does the type of soil or the type of foundation change the way a building is constructed? Yeah, absolutely. So those are some different things to think about on that. Okay, so I'm going to stop the recording for this part, and I'll make a second recording for our example problems that you'll be turning in later.